Here I have a very nice vintage synthesizer. It's the Univox model K-1. That's kind of an interesting nomenclature because this is also a Korg 700. Not a 700S, but the 700, meaning it has only one oscillator. This one is from 1973 or so, and it does not work. So I'm going to open it up and give you a tour of the insides, do a little visual inspection, see if I get any ideas about obvious problems. Right now I'm just flipping knobs and switches. I have already lubricated these. They're not great feeling, but I have every confidence, that most of the sliders are still going to work just fine. Switches feel good. I know the insides can be cleaned. Let's get to it. Now those are Mirage screws, so I gotta find another place. Here we go. Ooh. This is fantastic whole leaf tea from Thailand. They don't pay me, they're friends of mine. Love some tea. I'm missing a screw or two. That's a common, very common. Might be metric, but it's common, easily available. So there's not just screws in the edge cheeks, but also washers. So there's a metal plate, so this is just for show, it doesn't even protect the insides. There's a metal plate underneath the end cap. So you first take off the caps, or cheeks if you prefer. Right. Okay, so solid metal plates, both ends. This top piece will have to come off. It overhangs the back. Yeah, so the top. We'll go to the top right now. That'll probably be the most interesting view you can get. Different size screws here, and kind of like a sheet metal screw. Even smaller little screws on the back. These are just regular machine screws. right. Oh, this is for a sheet music holder, in case you're wondering. Not real exciting. I thought I might see a little bit more underneath here. You can see it's got webs inside of it. No surprise there. So this has a little door here. It's kind of cool. And inside the compartment is where the power cord gets stored. So this is the main fuse right here. I am curious about the status of the fuse. If the fuse is good, then, well, then I probably don't have any bad shorts inside, or the shorts are protected by something that completely blew up and went open circuit. But if the fuse is bad, then I know I've got some other electrical problems. Let's get a good contact here. The fuse is good, friends. I'll even put on audio so you can hear. That's my fuse. Okay, that makes me pretty happy, to tell you the truth. This is me happy. All right. More screws. Okay, so this wooden piece, the screw on top, and then the metal plate screws on the side go into it. Same story over here. So at this point I need to remove these other screws. It looks like, yeah, these side plates, they're not actually going to come off, I don't think, because they are spot welded to the back, which is a folded piece of steel which forms the bottom of the chassis as well as the back. So yeah, that's all right. It means that I should be able to do about everything I need just by going in from the top. Now, one thing, there is something important to see here. This is the bus bar for the keyboard, okay? And you can see all the resistors, one for every key. So I could check the resistance of this entire bus bar. It's going to be an interesting number. What am I thinking? We've got 1, 2, 3 octaves. I don't know. Maybe 3 meg? Guess we'll find out. We'll check what an individual resistor on the bus bar is at, resistance-wise. 400 ohms, 420, 400, 420. So we'll check it all now. 6.3 kilo ohms. Now the good thing is I got a reading. So the resistors in the voltage divider network for the keyboard are all connected. There's no breaks anywhere. Yes, I have found breaks in the past on synthesizers. So that's good. So we said 629K, and we said, so that's 6290 divided by, what, 37 keys? 170. That's not what I read. I'm going to have to take a look at these resistors. I'm not good at, I don't know resistor code, so let's put it that way, resistor color codes. I'm still getting about 400 ohms. I've checked a few of these. So I may have been reading an alternate path. Yeah, I just checked through them. So I was reading an alternate path of least resistance when checking the overall connection. But that's still all right. Let's make sure we're doing part of the physical inspection now. All these resistors attached to the bus bar. It's very important that everything's good there. Now there's another bus bar. There should be, I believe, underneath the key bed. So there's a couple of things going on here that I can't say I understand yet, but I will. This is not the bus bar that the keys, when you press down, the key creates a short circuit and connects the J wire from the key to the bus bar so that it reads just the voltage drop for whatever key you pressed. Presumably 1 volt per octave, but I haven't checked it exactly for this model. So we're going to press on. Again, everything's looking okay. By the way, I have plugged in and powered on this synthesizer. Nothing happens. No lights, no noise. The fuse is good. So what I'm going to say is there's a problem with the power supply. And I'm not surprised at all by that. Not a bit. So these are very long screws that come out of the top of the wood here. One thing you need to do, and that I'm going to be doing, well, in between breaks in this filming, is take some tabs on where do all these screws come from. I mean, obviously the video is a good record of that, but you know, you need a little more simpler record than this video. Now I just found all, what do we got, about 6 different kinds of screws right now. So that becomes a little, you know, a little trickier to keep track of. But that's why you take notes. So we're going to get these last screws out, and then it's going to be a real good time to take some notes. Exactly what screws go where. And I'll probably do a little cleaning up of some of the dust and stuff that I'm seeing right now just as I go. While I've got these out, I want to show you just a little bit about my methodology, shall we say. So this is the manual, the service manual for this synthesizer. It's a pretty good one. Block diagrams, pictures, parts lists, schematics. A little hard to read. The printout could be darker. I'm happy to fix that. I might have to reprint parts of this. You need this though. You need the manual. Before you even buy an old synth, make sure you got the manual. And then I have a logbook. Kind of thick. This is page 1 of a new logbook. I've got another one like this that is full of all of my synthesizer repairs for the last, I guess, about 6 years. So I don't do that just for myself as I go through the work. I do it for you because people contact me regularly about various synthesizers and ask questions about them. How can I fix this? How can I fix that? Do you have any information on this? And I've got a lot more details in some of my written logs than I'd ever put into like a video or put onto even a blog, because I'll have things like voltage readings at different points, not just the usual test points. I may have notes on potential mods. I may have some additional more detailed photographs that have helped people in the past with various projects, whether it was identifying a model of a DSP and of Axis Virus B, so that this team of software engineers who've made a emulator for the Virus B, could figure out what they needed to emulate in some of the models. So it's been surprising, all of the utility from taking the notes. I just took notes on all the screws, where they came out from. Make it simpler to repair and also to identify the ones that are missing. Now, clean? Not clean. That's just dust. But it won't come off without a cleaner being applied. Some great cleaners, just mention while I'm here, is Armor All is an amazing cleaner, and not just for plastics. Armor All will remove what's called craze from metal. So metal will get strange gunk on it. And the black keys are as dirty as the white keys, even though you can't see it. So, you gotta get them all. Craze looks like some weird coating glaze on metal. I ran into it on a Roland 1000 SH, neat vintage synth, and I had no idea how to get this stuff off, and Armor All did it. What I'm using right now is just some other car cleaner. So we got those screws out so we can get in. These keys. This is just like an initial superficial cleaning, because now we see something interesting. Because I'm gonna have to just take these all out. What? Oh, well, that's curious. We'll figure that out in a second. All the keys are gonna have to come out because I know that the edges of them, I'm looking at an edge right now, you can't see it, but it's filthy, as might be expected from years of use and years of spilling and whatnot. So this is just the initial going over, and then I'll clean each key by hand. I don't polish them. I've seen some people polish them. I mean, I don't mind the vintage look. Yeah, let vintage look vintage, because that's what it is. Okay, so somebody did something here. Oh gosh, it's amazing. This is just amazing. How you get such big globs of fuzz. There's the main fuse. The main fuse is good. What I'm looking at right now is 3 other fuses in the system, and none of them are in fuse holders, which is kind of a drag. Sometimes I'll put in a fuse holder if there's a place to put them in. In this case, it's not really a place to insert a fuse holder, so we're just going to test them. Good fuse. Good fuse. Oh, okay. Not good fuse. So, I can see. Check that again. I can see the filament, I think. Anything? No. Okay. So, bad fuse. Now what is going on here? This is a fuse holder. And as you can see, it's empty. So I don't know what the story is here. This is kind of strange because it's in parallel with this dead fuse, which doesn't make a whole lot of sense. The solder joint on this end is completely bad. It's just loose and swinging around. Actually, on both ends, it's broken. So this almost looks like somebody set up a bypass rig to bypass that fuse instead of replace the fuse, and then did a bad job doing it. That's some engineering talent. Okay, so now as I get deeper into this, I see some more this should lock together, yeah. Okay. I see more disassembly that has to happen to get where I need to get. So the metal frame of the keyboard is attached to some stanchions, we'll call them, that are screwed through the bottom of the case. So you don't take the keyboard off the stanchions, you take the stanchions off the bottom of the case, because that's the only way they're going to come off. Now, one thing to note while doing that, you gotta pay attention to where all the other connections are, because you'll often find you don't have a whole lot of margin for removing these things. So right now what I'm looking at is the keyboard wiring as it connects the keyboard to the main circuit board underneath it. Actually, there's two main boards. There's 19 and 18. Actually, 20 is the power supply. So transformer, power supply. The transformer. Well, I'll just tell you, this is interesting. So this is main power coming in. Okay. And why is there a second fuse? I don't know yet. We'll have to think about that one. Then it's a multi-tap transformer, so there's more than one place on it. We need to do some more dust removal. There's more than one place where the that might do it. You can tap the voltage off it. So the transformer has a bunch of windings in it, and those windings take the input power and they transform it down to a lower AC voltage. So AC in at 117 or so, and then AC out at the voltage required for two different voltage rectifying circuits, which would be on the power supply board. So multi-tap means you take the power off at different locations in the windings. So you get different voltages coming out. So that's why there's so many wires. So there's 1, 2, 3, 4 wires coming out of the transformer and 2 going in. So that tells me it's multi-tap. And we'll just have to think about this interesting relationship here. Gosh, I can't see this does anything. The black wire comes in from the main power. The white goes to the power switch. Red comes back from the power switch. And then right in to the transformer. And this black one goes through the fuse to this other black wire. Okay, so there's another fuse there. So the fuse nearest, this is a good point about fuses, the fuse nearest the fault, assuming there's a fault in the board, right, to cause the fuse to blow, the fuse nearest is supposed to blow first. It should have a lower rating than the main fuse. So I'll be able to take readings, actually read the fuses with a magnifying glass and see what they are. Now, two of them, these ones are labeled. So, half amp, 250 volt. Looks like could say a 32 millimeter fuse. So, large, on the large side, not a small fuse, but still pretty normal for fuses. I don't like that one being so close to the metal chassis. Wow. I hate that. You could almost mechanical jar this thing and have it touch. We'll look at that later, make sure it's got clearance. This third fuse, the mystery fuse here, there's no rating sticker anywhere. So it makes me wonder. And then this thing that provides an alternative path through it, well, that makes no sense. Okay, so we got to flip this up on its side now if I want to get deeper into the synthesizer, which of course I do. And you want me to also. Ooh, 117 volts. Oh, this is interesting. So while I lifted it up, I just found where the other fuse sticker is. It's on the vertical panel, and it's also a half amp 250 volt. So that all three of those fuses are supposed to be there. This is some oddball contraption that I don't understand, because it does nothing. And when I was looking in the circuit boards, they say Korg, by the way. Yeah, they do. Not only that, they say MiniKorg 700. Okay. Well, that's a great view. That's real helpful, Eric. Okay. So I said I've got to remove the stanchions. Let's see if we can show you. So there's two screws there, two screws at the bottom. These are big heavy screws. Once these are out, the keyboard itself is going to float free. So I've got to be careful, right? Oh! I knew I heard something a second ago fall out, but I didn't see anything. And I just found this mysterious extra component fuse on my workbench. That was kind of stupid of me. So this is a special fuse. It's got different mechanism, and it looks totally dead. Yeah. Yeah, it's dead. Whatever it is. Curious. Maybe this is what was in the extra mystery holder. Well, we'll figure out what that is later. So as I was saying, removing the keyboard, it's a careful operation because it's going to want to come out and be completely free, and I don't have any slack. I mean, no slack. So I may have to make some slack. So there's a wire bundle here from the keyboard, and there's a little key restraining clamp, which, oh gosh, if it's like the other one, yeah, it's screwed into the circuit board. Sorry you can't see this fun activity here, which means I can't oh, maybe it's just flat out screwed in. If it's just screwed in, we'll just remove it. I was just wondering if maybe there was a nut underneath it, a retaining nut. One thing to note, I'm using an electric screwdriver. I know some people freak out. Oh my God, don't use an electric screwdriver on vintage gear. I'm only using it to take stuff out, okay? I don't use it to put stuff back in because I don't want to crack anything. Okay, so here is, this gives me a little more slack by removing this so that I can get the keyboard out without as much concern. So we will take out the top two screws first. They're thick, heavy screws with washers. Not real long. 3/8 or so. Okay, the keyboard's already wanting to come falling out, but I'm holding it with one hand as I do this. So. These have toothed washers so that they hold better to dig into the metal. Okay. Keyboard is free. So let's have a look at what we've done here. Make sure we got some slack. So we pull it carefully. Now, there should be nothing else connected, but I'm checking because I've never opened this up before. Okay, there's just one set of wires. Fantastic. And since we already removed this piece right here, for the screw in it, that enables the slack I need to move this forward and get it on the workbench. Put a couple things away. Again, you can see probably more than ever. Actually, I just put away the air duster I probably want to have, right? Because, where does it come from? We'll have to wipe this down because, you know, blowing them around doesn't necessarily get them out. All these dust bunnies. Now, I'm curious, what do we got underneath there? Just give a quick look. All right. Okay, that's interesting. So, the same principle as J wires, but no J wires. It's done with little brass plates. Guess that's what they are. Now, I'm just listening. I'm looking now at the curious bushings. So these are the key stops underneath the keys. The key stops have bushings on them, and the bushings absorb the key press. They all sound good. They all feel good too. If the bushing was bad or missing, then the key would be hitting the metal key press, and you would hear a definite clunking sound, very different sound. So that will tell you right away if you're inspecting a keyboard before you even open it up. You can tell if you have good bushings or not. I don't know what they made these out of. Maybe they were new, maybe they've been replaced. But those are in good shape. I don't see any dry rot or anything like I have seen on other bushings. Well, that's good. Now what I don't see is how these things work. I'm completely missing something about the mechanism. How this works. It looks like, yeah, this is a slightly different mechanism. There is, yeah, that's okay. So I was expecting like one long bus bar, and when you press a key, it presses the little metal piece, right, whether it's a J wire or something like this, up against this bus bar, and then that creates the circuit through that segment of the bus bar from where the voltage enters the keys, and so it goes to the bus and makes a circuit. So this is doing the same thing, slightly different fashion. I'll try to show you. So the voltage comes in, and say I press the first key, just make life simple. How does that make a circuit? That's a bad example. Maybe the second key? No, it's still a bad example. I may be at a loss on this. Well, what you can't see on the video, but what I can see here is in each of these little plastic segments, which have 1, 2, 3, 4, 5, 6, what, 7 keys or so in? Can't just be 7 in each one, can it? 8. It's gonna be, yeah, whatever. There's a metal bar, okay, in every one of these. So when you press the key, this is touching that metal bar. Now, that in itself doesn't seem real exciting, but it's got to have something to do with the mechanism that I just don't understand. I don't understand yet how the switching works in this. I think they're, oh, I found it. Okay, so the lights just came on in my head. This piece is skinny and doesn't have the 2 prongs, and there's only one in each of these segments is connected to this brown wire. So the brown wire is soldered into each of these. This is in constant contact with the metal bus in each segment. So that's our voltage path. So when I depress a key, the signal, the circuit created, comes in. So I'm pressing this one here. Up that key, and then along the bus to the center point, which is connected to it, and back out to this brown wire. And what that's going to give you is an amount of resistance that the voltage traveled through. Well, it's going to give you the voltage actually, but the voltage is dropping because of the resistance. So if it's the fifth key, it'll be 1, 2, 3. There's another one under there you can't see, 4, and 1, 2, 3, 4, 5. Fifth key, fourth resistor in. So the voltage is dropped down by the current times the amount of resistance there, and that gives you what the new voltage should be and tells you what key was pressed so that you can run your oscillator and produce the correct frequency. V equals IR. So, gosh, a lot of dust bunnies. Gotta be careful. No, be careful. Don't break the transistors. So what I'm going to do now is give a tour of what you're looking at here, because you're looking at some technology you probably haven't seen. It's not going to make the most sense unless I explain what you're looking at. What's this? Is that anything? Where did it go? Ooh, it's gonna take, oh wow. That slider, the back of it is so dirty I couldn't hardly see it. Oh, that's a little piece of paper floating around in here. What do we got? I have no idea. It's not labeled. I don't think I need it. It's paper. So really dirty in here, as expected, no big deal. The switches, oh, these are neat mechanical switches. They have gears in them. That is awesome. Wow. Gears. Those will be easy to test to make sure that they, work as switches. So this is different resistances coming off the different positions of the switch, and multiple in some cases. That's a little fancy. This other one is more about positions than, oh, that makes sense. Okay, so this one was selecting the waveform. This is changing the footage, which is a term derived from pipe organs. So 32-foot pipe, that's your very low, deep note. And then an octave above that is half that pipe length. So that's the 16-foot, 8-foot, 4-foot, 2-foot. So these different resistance values in there, that may be all it's doing, is providing the different resistance value to the oscillator when it's giving you the frequency for the key. Okay, I said a tour. I gotta do some inspection as I tour through this myself too. It's just so dirty. All right, we already know transformer, multi-tap transformer, dead fuse, missing fuse. Then I found the fuse. Don't know why this is here. I will look in the schematic from my books to see if that's supposed to be there or not, and figure out what on earth is going on. Now, this is a power supply unit. I mentioned we've got a multi-tap transformer. Well, that means we have two different voltages coming off the system. So we've got calibration. The larger capacitors in the power supply are typically filter capacitors. So after it is rectified by these 4 diodes here, which form what's called a full wave bridge rectifier, what that effectively does is when you have AC, right, you have a sinusoidal wave. So the rectifier, it flips the negative waves up. So you get 4 humps in a cycle, all positive. And then these big capacitors are used to filter and smooth that out so that you get a steady voltage coming out. That's the gist. Now, power regulator. So I get my voltage rectified. So now it's no longer AC, it's DC. I smooth it out. And then I'm going to regulate it. Power regulator, I would say that's a voltage regulator. I'll double check, but that's what I believe. I can't read the numbers on these other guys with the heat sinks. They're not just like a standard voltage regulator. They still could be a voltage regulator. We'll figure it all out. But that's the gist of the power supply. You can calibrate it a little. You got the rectifier, filter capacitors, transformer. That's your main, power supply system in virtually all electronics that has any type of transformer. There'll always be some other DC voltage converters inside that ultimately give your components what they need. Now, this is from the early 70s. So one thing you don't see, other than these 3 boxes, which we'll talk about separately. Oh gosh, huge dust bunnies. You don't see an integrated circuit anywhere. Not that they didn't exist, some existed. But actually, I do see some. I'm lying, there are some. This little metal can, and that little metal can, if you look at the number of leads that they've got, you can't see it, but there's a lot of them. Ooh, the circuit board is labeled. That's fantastic. I love that. So this is an op amp. This is a 741, and this is a MN133. So that's a Matsushita, which is bought by Panasonic, and hard to find. They don't make them. It's a divider. It's a frequency divider. And that makes sense because this piece right here, which is labeled IC, and KEIO, that's Korg. It's abbreviation. So this is a potted IC, like a potted plant, inside these plastic boxes, which are also, like unobtainium, is a little circuit board. I think it's a separate board. And on that board are discrete components like what we're looking at here. Transistors, capacitors, resistors. If you decapped a modern IC, that's what you're going to see. You're going to see transistors and capacitors. Ooh, there's some diodes. They're all inside this box. And then they pour plastic in the box that hardens and surrounds all the components. The point of that was to prevent people from stealing their designs. So this is an oscillator. This is a high-pass filter. This is a low-pass filter. Now, the nomenclature is the same on them, and I believe it's how they're wired up, which determines what their functioning is. Now, I've done a lot of research on this synthesizer and a related one, the MiniKorg, before buying them, before opening them up even. And there's some curiously talented people in this world who have sat down, taken these things apart, whether they've had like broken ones, and chipped them all the plastic out to get to the components, and then reverse engineered and documented what the circuit boards and the components look like, so that you can build a new one. Yeah, I've got diagrams photos and stuff of that process that would enable me, if necessary, to build one. Kind of interesting, huh? So, what can I say about this? Calibration, okay? Oscillator calibration, filter calibration. You can see some of these have been turned, huh? Normally you would see like that blue pen and the blue dot lined up. Okay, and it is. Then I go over here, red and red. I go here, wait, red's over here, but the red dot's there. What? And this one, same story. So these have been completely tweaked. Why, I don't know. I mean, but something has changed, right? Something has changed. What is that? No, that's nothing. All right. A lot of fuzzy stuff. One thing I wish, but that I don't have, I don't get my wish, is that there's a plug that I could just unplug this power supply and test it without it hooked up to everything else. Because it could be a fault on these boards which is blowing a fuse, right? Or it could be a fault, you know, in here. These may just have to go anyway. This is old. It's almost as old as me. So some of these, you know, you can kind of test in place. That's not really the best way to do it. Best way is take them out. If you take them out, geez, you might as well replace them. 470 microfarad. Yeah. Okay. These are the same filter caps as used in an ARP axe that I just worked on, actually. I think that was the same rating. Power supply is different, though. You know, this is interesting. I was thinking that this was, you know, power regulator. Well, yeah, it is, but this is an IC. So this has some sort of, if it's like the ARP axe, which also has calibration, IC, output, power transistors, bridge. That IC is smart. It senses and can control the voltage so that if something goes wrong, it's supposed to kind of compensate to an extent. But if it fails, like it did in the ARP axe, then all bets are off and other things will fail on the board. Now I do see my friend Mr. Tantalum Capacitor. These guys, these little red ones, nestled here and there. I do see a ton of transistors. Jeez. The reason there's so many transistors is because you don't have ICs, effectively. At least not modern ICs. Look at a little package. Got these big ones. Wow. What's can I say about the switches? Cool switches. big monster heavy duty sliders. I'll be able to take readings on all of them to see if they're good or not. Oh boy. How? How to test this thing? Well, just don't know. We got high and low outputs. It's only one line, so the only difference is there's resistors, different resistors. One has a capacitor as well, which change the characteristics of the output. There's very little I can do without coming up with a scheme of how to safely depower things before turning things on. So ground, positive volts here, negative volts there. And I'll verify all these with the diagrams and the schematics. Negative volts, ground, positive volts, ground again. Why you need more than one ground, I don't know. But that's not untenable. So the smart thing to do, looks like for me, will be to desolder. And luckily it is on the top of the circuit board. I like that. That makes it easy. Desolder the power lines. Okay. Make sure that they're not touching anything. Once I get them desoldered, you can put a little cap on them if you want, or some tape. And then this will be isolated, and you can power it on. That's what I want to do, because I want to test this power supply, step one. This capacitor, by the way, has a really big bump on his head. Not just a bump, it looks like it's it almost looked like it was cracked. So that doesn't look good. It doesn't mean it's bad, but it means take a look at it. That's interesting. I don't know what that is. Wow, okay. Some people hate all these old lilac capacitors. I'm not sure why. These are from the 70s. They're not the ones from the 90s that were made of a bad formula which caused them to leak, ruin gear. Now this one, that's swollen and cracked. Shining the light. I'll be getting on a magnifying glass at some point, I'm sure. Shining the light is, and looking real close at these things, will give you some ideas of what might be wrong, or what you should definitely take a look at. When things are clearly cracked or swollen in odd ways. Transistors are exploded, because they do. These are all good though. At least they're not exploded. I'm not seeing burnt resistors, which is good. People talk about the tantalum capacitors and that they can burn up, explode, and all that. Yeah, they can. They don't have to. I've replaced bad ones that had no signs whatsoever of being bad. They were simply shorted out because they were maybe in the wrong place at the wrong time. Okay, so cleaning, removing power leads so that we can power this on and see what's going on. switch testing, taking readings off the sliders. Those are the things we can do without doing much of anything else. You know, there's a lot to be done on this before you can even get into trying to repair it. So that kind of concludes the tour, my thoughts about the approach to this particular synthesizer. Yeah, and you got to have an approach. You've got to work out in your head how you want to disassemble things to facilitate testing individual modules. So I'll tell you, like, if this power supply is good, right, then I could reattach the wiring for the oscillator board. Okay. Leave the filter detached. Power it on and see what the oscillator does. Because if you think about it, you know, all the synth architectures are inherently modular. Power supply module, oscillator module, filter module. So yeah, you approach it piecewise and try to figure out where your fault is, okay? And then if, you know, naturally if this tests well, I should also see it, since it is the oscillator, I should see it responding to the keyboard, right? So that will enable me to test that easily. I mean, there's a lot of ways to test a keyboard. I mean, I could just plug the keyboard into another modular synthesizer. Done that before, it works fine. It's a good way to test them. So, more dust, sorry. If that's all good, then move to the next piece. You can kind of assume that there could be something bad on this piece, right? Since I operate under the assumption that fuses don't, you know, open circuit on their own. They get a little help, right? So we need to find the component that is causing it to go, and sometimes that will cause some other things to go around it. So it'll be pretty interesting. Like I said, you can do a lot of testing without energizing it. But at some point you gotta, which is why I want to have this strategy of how to isolate the boards and individually test them. All right. So that is the tour of the Univox K-1, also known as the MiniKorg 700. This came out in 1973. I hear this was one of the, I guess, more favorite synthesizers of the Cars. So that alone tells me I want to hear this thing, get it fixed up, and then you know, have some fun with it. If you have any questions, leave them below.